When an object is placed in front of a spherical mirror, we can determine the location, size, and nature of its image by using the technique of ray tracing or the mirror and magnification equations. Both options are based on the law of reflection. The mirror and magnification equations relate the distances dO and dI of the object and image from the mirror to the focal length f and magnification m. For an object placed in front of a lens, Snell's law of refraction leads to the technique of ray tracing and to equations that are identical to the mirror and magnification equations. Thus, mirrors work because of the reflection of light, whereas lenses work because of the refraction of light, a distinction between the two devices that is important to keep in mind. We can derive the lens equation and the lens magnification equation by analyzing the geometry of the rays used in the ray tracing procedure we use to find the locations and orientation of the images. We start by looking at the ray drawn from the top of the object through the center of the lens. Since it does not bend when passing through the center, we see that the angle the ray makes with the principal axis, theta prime, is the same on both sides of the lens. Both the object and image are perpendicular to the principal axis, and therefore the shaded triangles formed by the ray, principal axis, and the object or image are similar triangles, meaning that they all have the same angles, although the lengths of their sides differ. For the triangle on the left, we have tangent theta prime equals HO divided by DO. For the triangle on the right, or image side of the lens, we have tangent theta prime equals negative HI divided by DI, where the minus sign arises in the numerator since the image is inverted and to ensure that tangent theta prime is a positive quantity. We can now write HI divided by HO equals negative DI divided by DO, which equals M, where M is the magnification, and this is the magnification equation for thin lenses. Next, we analyze the geometry of the ray refracted through the focus on the image side of the lens. The angle between the refracted and principal axis is theta, and the object and image are both perpendicular to the principal axis. This means that the shaded triangles are similar, and we write tangent theta equals HO divided by F, which equals negative HI divided by DI minus F, where DI minus F is shown here as the distance between the image and the focus. We can rearrange this as DI minus F divided by F equals negative HI divided by HO. From the magnification equation, we can write the right-hand side as DI divided by DO, and with a little algebra, we can write this as 1 divided by DO plus 1 divided by DI equals 1 divided by F. This is called the thin lens equation. When applying this equation, care must be taken to use the proper signs for the various parameters. The following conventions hold. Regarding the focal length, F is positive for a converging lens and negative for a diverging lens. The object distance, DO, is positive if the object is to the left of the lens, a real object, and is negative if it is to the right of the lens, a virtual object. The image distance, DI, is positive for an image, which is real, formed to the right of the lens by a real object. It is negative for an image, which is virtual, formed to the left of the lens by a real object. Finally, the magnification is positive for an image that is upright with respect to the object, and negative for an image that is inverted with respect to the object. We now demonstrate the application of the thin lens and magnification equations through an example. Suppose a 4.00 centimeter candle stands 11.0 centimeters in front of a converging lens of focal length 2.50 centimeters. A. Find the image distance and determine whether it is real or virtual. And B. Find the magnification and determine whether the image is inverted. We start with the thin lens equation and rearrange it to give 1 over DI equals 1 over F minus 1 over DO. This equals 1 divided by 2.50 centimeters minus 1 over 11.0 centimeters. This equals 0.309 inverse centimeters. Or, inverting, DI equals 3.24 centimeters. Since the image distance is positive, the image is real. For part B, we use the magnification equation, M equals negative DI divided by DO, which equals negative 3.24 centimeters divided by 11.0 centimeters, which equals negative 0.29 centimeters. Thus, the image is smaller than the object since the magnitude of M is less than 1, and the image is inverted since M is negative.